Alright, welcome to the NUPOC Video Study Guide number 22. So let's look at question 19 in the General Math section of Guide 1, which very directly asks us how is e, the base of natural logarithms, defined. So this should be pretty quick. There's a couple ways to define it. Number one is probably the more common way. It's taking a limit, and it's sort of a similar form to what you see in compound interest problems. And that's simply taking the limit as x goes to infinity of 1 plus 1 over x to the x. So the way this works is, as x becomes a very large number, this 1 over x becomes very, very small, and so this whole parentheses becomes very, very close to 1. It starts to approach 1, but at the same time, this exponent is becoming very, very large. So, you're taking something like, 1 plus 0.001 to the 1,000 or something like that. And so, as you take the limit, as x goes to infinity, this whole quantity will approach 2.71, or e. Now, there's another way to define it that is actually an infinite sum. So we could also say, let's actually write e equals, right? E equals. And there's an infinite sum notation that basically just says e equals from n equals 0 to infinity the sum of 1 over n factorial. So similarly, as n gets very large, this 1 over n factorial gets very small quickly, and so you're adding up all these very small numbers to infinity, and eventually it will converge to e. So these are two ways that you can define e, the base of natural logarithms. So that was pretty short, and so I'm going to take a quick aside in this video to do a quick little proof or derivation or what have you for an equation that I kind of like and I think is pretty elegant, even though it's actually not a problem, not one that I've seen yet, at least in the NUPOC study guides. So there's kind of this really interesting equation, probably some of you have seen it, that relates 5 of the most important quantities in mathematics, and that's e to the I pi plus 1 equals 0. So that's pretty cool, to be able to say that. So we've got e, right, which we just talked about, raised to the I, the imaginary number I, times pi, right, another very important constant, plus 1, which is the what would that be? The well, unity, multiplication, unity, and then 0, right, which is also a very, very important quantity. So we have this equation which is true that relates all 5 of these quantities and nothing else, which is really, really cool. So how do we show that this is true? Well, we can use Euler's identity, basically, right? Which says, right? So Euler, right, says e to the, say, I theta equals. We're just basically converting between polar and rectangular coordinates, really. So what we have is e to the I, and we could even put some sort of amplitude out here. A e to the I theta, right, equals a times, well, we'll just put it on each factor, cosine theta, right, plus, let's put it inside the j, a sine theta. Right? So here our a is just 1, so we don't really need to worry about that. But let's plug in pi for theta, right? So we'll get e to the I pi equals cosine pi plus j sine, not theta, pi. Okay? So if we look on our unit circle, right, here's here's pi right here. This is pi over 2, and this is pi, right? So if we go out to pi, we'll see that, well, the sine of pi is 0, so this goes to 0. Cosine of pi is -1, so e to the I pi just equals -1. So -1 plus 1 equals 0, right? So we can check it. So anyways, that was sort of a short problem out of the guide, so I just wanted to take a quick aside there and show you something that I think is pretty cool. But what we really came here to learn is this. So while this is really cool, this is also true. So keep this in mind as well. 2 ways to define e, the base of natural logarithms. And a cool little equation over here that relates possibly the 5 most important quantities in mathematics and nothing else.